Okay, ladies and gentlemen, it is time to stop talking about a derivative at a point. So, for example, recall if I asked you for the derivative at x equals a of a function f of x, then we know that that means f prime of a, that's what that means. Geometrically, it's the slope of the tangent at x equals a, and by definition, it equals f of a plus h minus f of a over h, and all of this is dependent upon if the limit exists. And again, that's a little bit of a scary statement, and I haven't really explained it yet, but this is what we know. So, and we ran around doing wonderful examples. And so if I told you that I wanted you to do it, and I'm not going to redo this one, but let's say I gave you f of x equaled 2x squared plus 4x minus 1, and if I wanted to know the slope of the tangent when x equals 1, then you would have to do f prime of 1, which is the limit, as h approaches 0, of f of 1 plus h minus f of 1 over h. And you'd have to work all that out. And then if I came along and if I said, okay, I changed my mind. I don't want to know it when it's x equals 1. I want to know it when x equals 2. Well, then you'd have to do the equation f of 2 plus h minus f of 2 over h. And you'd have to work all that out. And it would be a different answer. It would be a different slope because the tangent has moved along that curve. And then what if I got even nastier and I said, yeah, I changed my mind. I'd like to know when x equals 7 now, if you don't mind. Well, then you'd have to do f prime of 7 with the limit as h approaches 0 of f of 7 plus h minus f of 7 over h. And are you getting the point here? I have to keep doing it for each and every point. And I have to keep doing it over and over and over. And that is crazy. But that is the essence of a derivative at a point. What we would like to do now is do the derivative in general for the entire function, for any point. And that's a little bit different. So we're going to be asking you to calculate the derivative when x equals any value of x on the domain of f of x. And that's a much bigger question, and it's a much more useful tool. So we're going to be finding a new function, and it's going to be giving us the derivative everywhere on our original curve. So what we're going to be talking about is the derivative of a function. The derivative of a function is a new function. That will give us the slope of the tangent to f of x at any value of x on the domain. And this new function looks like this, f prime of x. So the derivative of a function, which we write as f prime of x, is a new function that will give us the slope of the tangent to f of x at any value. So So that takes us to a definition. The derivative of a function f of x is a new function f prime of x such that the limit as h approaches 0 of f of x minus h minus f of x over h equals f prime of x. And you will see this written in another form, but it means the exact same thing. Let's say I didn't want to use h as that little bit that I move down the x-axis. Let's say I wanted to use delta x as that little bit. Oh, did I put a negative here? I'm terribly sorry. Please change that to a plus. And those two formulas are identical, just changing the variable that we're using for adding just a little bit more x value. They are identical. And remember, all of this is incumbent upon provided the limit exists. So there's your definition. So I'm going to go back to the examples that we've done earlier today, and I'm going to find the derivative function of the original function. So given f of x equals 2x squared plus 4x minus 1, determine f prime of x. So it's a new function that we're finding. What you would do is you would write f prime of x equals the limit as h approaches 0. I'm just comfortable using h's, so I'll continue. F of x plus h minus f of x all over top of h. Now the difference here being is that we're not taking it at a specific point. That x value is not a number now. It's going to go in everywhere there's an x as the following. It'll be the limit as h approaches 0 of 2x plus h squared plus 4x plus h minus 1, all subtract 2x squared plus 4x minus 1, all over top of h. The algebra is the same, so it's 2 times x squared plus 2xh plus h squared plus 4x plus 4h minus 1, all subtract 2x squared plus 4x minus 1, all over top of h. Limit as h approaches 0, so this is going to be 2x squared plus 4xh plus 2h squared plus 4x plus 4h minus 1, taking that negative in, minus 2x squared minus 4x plus 1. Running out of room on this page. Limit as h approaches 0, 2x squared minus 2x squared, negative 4x, positive 4x, positive 1, minus 1. So I'm going to be left with 4xh plus 2h squared plus 4h over top of h. Notice if I allow h to approach 0, I still get 0 over 0. So I still have some work to do. How do you want to do this? Well, I think I can common factor an h out of the top, and it will reduce with the h on the bottom. So limit as h approaches 0, take the h out. 4x plus 2h plus 4 over top of h. These h's will reduce, getting rid of the 0 term. I'm going to turn the limit on. H approaches 0. That h approaches 0. So now it's 4x plus 4. The limit's gone. Put my equal signs in. And what we know is that the new function f prime of x is equal to 4x plus 4. And that is the derivative. That is the slope of the tangent for any value of x on the original function f of x. So that's important. This is a new function that will give the slope of the tangent to f of x for any value of x on the domain of f of x. So, if I wanted to know the slope of the tangent when x equals 1, which I think was our question. What did we do? Was it at 1? What we did earlier today?
I think it was 2.
Was it 2?
Yes.
Okay, so, and do you have the answer?
Yes, 12.
So the answer is 12. So we learned earlier that the answer is 12. Let's see if it works here. F prime of 2 will equals 4 times 2 plus 4. Lo and behold, it equals 12. And so then if I told you that I wanted to know when x equaled 7 instead, you would do f prime of 7 equals 4 times 7 plus 4. Oh my gosh, I picked a number I can't do. What's that, 28, 32? Okay. And that's how that works. I'm going to stop the video here and I'll be right back.